Hey there, and welcome to this explainer. Today we're doing something just a little bit different. Instead of dropping a dense, overwhelming textbook lecture on you, we're going to peacefully decode the grammar of electrical circuits together. We're going to explore the core rules of electrical engineering in a really calm, structured way, actually looking at the notes and equations that build this whole thing from the ground up.
Think about the device you're watching this on right now. How do we actually make sense of the invisible forces powering it? When you stare at a raw circuit board, it can honestly feel like magic or just, really intimidating math. But at its core, electrical engineering is not chaos. It's just a beautifully elegant system of natural rules. Once you get the alphabet down, you can read the language without breaking a sweat.
So here's our roadmap for today. First up, the spark of electricity. Then we'll look at active versus passive elements, followed by classifying circuit elements. After that, we hit the rules of networks, and finally, analyzing circuit behavior. Nice and simple.
All right, let's just dive right in. Section 1, the spark of electricity. Charge, current, and potential. Everything starts with charge. It's literally the characteristic property of particles. You've got protons carrying a positive charge, electrons carrying a negative charge, and neutrons just hanging out neutrally in the middle. We measure this in coulombs, and this fundamental property of matter is the reason any electrical phenomenon exists at all. To put that into perspective for you, a single lightning bolt, that contains roughly 15 to 350 coulombs of charge. Without charge, literally nothing happens. It's the absolute bedrock.
Now, once we actually have charge, we can get it moving, and that gives us electric current, which we represent with the letter I. This is simply the rate of flow of electric charge over time, measured in amperes. Honestly, the easiest way to picture this is just water steadily flowing through a pipe. The more water moving past a specific point every second, the higher the current. The wild thing is, the individual electrons aren't zipping around at light speed. They actually drift pretty slowly, but the energy wave pushes through the circuit almost instantly, delivering power the exact milliseconds you need it.
But, water doesn't just flow through a pipe without water pressure, right? And that brings us to electrical potential, or voltage, our letter V. By definition, this is the amount of work done to move a unit positive test charge from one place to another. So the big takeaway here is that voltage is the work. It's that invisible pressure required to actually push the charge forward through our metaphorical pipe. It is the driving force behind the whole flow. Okay, moving on to section 2, active versus passive elements. Let's meet the players on the board.
In any electrical network, components basically fall into two distinct camps, and it's super important to draw a clear line between them. On one side, we've got active elements. These are the guys actually supplying energy to the circuit. Think of the battery in your smartphone pushing out power to make everything run. On the flip side, we have passive elements. They don't generate any energy at all. They just consume it, dissipate it, or maybe hold on to it for a split second. Think of your phone's screen glowing or the processor heating up.
I love looking at handwritten study notes like these because it really humanizes the math, doesn't it? You can see the three primary types of passive components mapped out right here. We've got resistors, which dissipate energy as heat, inductors, which store energy in a magnetic field, and capacitors, storing energy in an electric field. These three are the main characters you're going to run into in almost every schematic. They dictate exactly how energy is used the second it leaves the power source.
Let's build out that mental filing cabinet a bit more. Section 3, classifying circuit elements.
First up, we can categorize these elements by how they handle direction. Unilateral elements have behaviors that totally depend on the direction of the current. They're basically one-way streets. Diodes are a perfect example of this. They only let electricity flow safely in one direction. Bilateral elements, on the other hand, are super chill about direction. They allow flow either way. A resistor is bilateral. You can literally take a resistor, flip it around in your circuit, and it does the exact same job, resisting flow evenly no matter what path it takes.
We can also classify them by their math. Linear elements perfectly play by Ohm's law. Their voltage and current scale together proportionally. So if you double the voltage, boom, you double the current in a perfectly straight line. Nonlinear elements do not satisfy Ohm's law in that clean, simple way. Think of an old-school incandescent light bulb. As it gets hotter, its physical resistance actually changes, so the relationship between voltage and current curves and wiggles around instead of staying perfectly straight.
All right, components defined and sorted. Let's get into the universal laws that strictly govern how they behave when we hook them all up. Welcome to Section 4, the rules of networks.
Check out this student note defining Ohm's law, which is pretty much the absolute bedrock of circuit analysis. V equals I times R. And honestly, it brilliantly shows the simple elegance of electricity. The current passing through a conductor is directly proportional to the voltage across it. It is incredibly reliable. Now, as the note correctly points out, it definitely has limitations. It doesn't really apply to complex components like semiconductors or vacuum tubes. But for laying down our foundational understanding, it is absolutely the master key.
And when we map out where all those currents actually meet up, we run into Kirchhoff's current law, or KCL. KCL simply states that the algebraic sum of the currents meeting at a node is exactly zero. In the most basic terms possible, whatever total current flows into a junction absolutely must equal what flows out. Electricity doesn't just vanish into thin air. It is a perfect, unyielding balancing act where every single electron is accounted for.
Now, just as current is perfectly conserved at a junction, voltage is perfectly conserved in a loop. If you look at this closed path, it beautifully illustrates Kirchhoff's voltage law, or KVL. This shows that the algebraic sum of voltages around any closed circuit always balances out to zero. It's kind of like a roller coaster. Whatever height the chain motor pulls you up to, you inevitably have to drop back down to ground zero by the end of the ride. The total energy supplied by your active elements perfectly matches the energy dropped across your passive elements. Nature always balances the books.
All right, home stretch. Section 5, Analyzing Circuit Behavior.
I know looking at a massive, tangled schematic can instantly induce a little panic, but it really shouldn't. Analyzing a circuit is just a calm, logical, step-by-step process. Step 1, you identify the nodes where current splits and the loops where voltage drops. Step 2, you apply those Kirchhoff's laws, KCL and KVL, to those specific spots. And Step 3, you just use some basic algebra to solve the resulting equations for your unknown values. You just calmly follow the rules, piece by piece, and the complexity just untangles itself.
But hey, what happens in the exact millisecond you flip a circuit on? Well, that's where transient analysis comes into play. These equations map out the DC response of an RL circuit. That's a circuit with a resistor and an inductor. Now, I know it looks like an intimidating wall of calculus, but it's really just a predictive tool. Think about flooring the gas pedal in your car. You don't hit 60 miles per hour instantly, right? Similarly, these equations just let us predict exactly how an inductor reacts the moment that switch is flipped, giving us the temporary transient curve and the final steady-state current. And when we actually graph that math out, the curve reveals something really cool. You quickly realize that all those dense equations are just describing a totally smooth natural rise in energy over time. Because an inductor naturally opposes any sudden change in current, the energy doesn't just violently spike to the top. Instead, it smoothly and predictably curves upward until it gracefully levels off at its maximum state. It's a gentle ramp-up, not a crash.
As we wrap this explainer up, I want to leave you with a really peaceful thought. Complex circuits are simply fundamental rules of energy and flow, just repeating at scale. No matter how chaotic a diagram looks, whether it's a basic flashlight or a massive, sprawling global server farm, it is entirely governed by these simple, beautiful rules we've talked about today. So, what does this all mean for you? Well, the next time you turn on a screen or flip a light switch, ask yourself, are you just interacting with technology, or are you actually witnessing the perfect, invisible, balancing act of the universe? Thanks so much for joining me, and keep exploring.